All right, good. So this is, let me share the screen, and you guys can ask, now that your camera's off, you can ask questions all you want. So today is, if you watched, and really I looked on YouTube, there was 0 views. So I don't think anybody's got a chance to see what I recorded Saturday yet. And that Saturday video took me, I think Eric jumped in at the very beginning on Friday. And then I ended up, Eric, not even recording it Friday. I spent about 3 hours putting together that video because it's such an important topic. So you definitely want to watch Friday's video, which was put out Saturday. This today actually was so important that I kind of went over a lot of the concepts in class today. So I don't want to repeat myself too much. I assume you can go back and watch that video, but I will hit some of the highlights.
Did you post those screenshots from Saturday on Canvas that I can use for notes?
I thought I did.
Okay, well, I haven't checked yet, so.
Yeah, they're there. Okay, so I posted some screenshots, but they're not as good as the screenshots from that. So now that you say that, I haven't posted screenshots from the day yet. I was going to wait and see what happened here, but yeah, I will post these. This goes more in order, so I will post these screenshots, which will look a little like Saturday screenshots, but these will be better. So I might just, I don't know, we'll see. Okay, so we started off class talking about the Solvay conference and talking about these people. This is 1915. I think it was one of the first ones. Solvay was this rich philanthropist. I don't think he really was a scientist. Maybe a lot of these rich people like to play like they're scientists. So he would invite all the greatest minds somewhere in Europe, the Solvay conference. But he would invite all the greatest minds to come and talk over today's problems. Well, this is 1915, and this guy right here was in the throes of developing general relativity. He had developed special relativity in 1905, but general relativity, so he was pretty much a hotshot, but not near the hotshot he was after the 1919 eclipse, when he was proven true for general relativity, and that space-time really is curved. So he was still a bit of an oddity then. He was still very well respected, just to be invited to the Solvay conference. But for one thing, do you notice any women in here?
Marie Curie?
Yeah, there's only one, and that's Marie. And Marie Curie is older there. She was actually in the throes of radiation poisoning. I don't think she lived much longer past that. So she was already kind of sick. Her and Einstein would take these walks in the woods together and just talk about physics and all. And Einstein reported that she was a bit of a grumpy old woman. Well, mainly because she was sick. Gosh, she felt awful. She, now I hate to talk out of school here, but Marie Curie and Ehrenfest had an affair, if I remember the book. She looks a lot older than he does, which makes me question my source, but supposedly they had a bit of an affair. It was all those hush-hush things. But this is after her husband Pierre had died. Little gossip there, physics gossip. Max Planck, right here. Max Planck, who is the father of the quantum revolution. He never really believed in the quantum revolution, but he was the father because he's the first one to start talking about quanta and this black body radiation. All these, man, there's so many huge. All these guys have formulas named after him and institutes and schools. There's Lorentz. Now, the reason why Lorentz is sitting by Einstein is the Lorentz transformations is what is the formula behind time dilation and linear dilation, which Einstein used in his special relativity. Here's Paul Dirac, and I have a book on my shelf back there called The Strangest Man, and it's all about Paul Dirac. He was a mathematician, as much as a physicist, but he developed a lot of the math behind like the Dirac equation, behind a lot of quantum physics. We have Schrodinger. Maybe you've heard of Schrodinger's cat or Schrodinger's equation. Schrodinger was of the wave. He was of there's you split your quantum into two categories historically. One is the wave mechanics, and one is matrix mechanics. And Schrodinger was leading the wave mechanics, where there's something called Schrodinger's equation. And when you take modern physics in college, you'll take mechanics physics, which is what this class is, with or without calculus, and then you'll take electromagnetics, which is all electric fields, magnetic fields, how they all go together. Basically, it's Maxwell's equations. And then you'll take modern physics. And when you take modern physics, about half of the class is Schrodinger's equation and how to use it. It requires about 3 years of calculus. Okay. There's Wolfgang Pauli. Now, if you know much about the Pauli exclusion principle, if you should have probably had that in chemistry, but if not, certainly in AP chemistry, where the idea of electrons and orbitals, it's Pauli exclusion principle. And then there's Heisenberg. His name's a little bit obscured there, but if you've seen Breaking Bad, he calls himself Heisenberg, in it because he's named himself after this guy. But Heisenberg was a Nazi, not by choice. He was forced in, back in the 1930s, late 30s. If you did not ascribe allegiance to the Nazi party, you got a bullet in the head, or you had to try and escape the country. So Heisenberg pretty much had to, and he was the greatest scientist. I think he would be right up there with Einstein and Schrodinger. He was one of the greatest scientists. He was in charge of the matrix mechanics. But look at the guy, man. You can tell the guy. I would hate to have to present in front of this guy. He'd just rip you apart. Plus, he was German. So he headed up the Germans' attempt to develop an atomic bomb. We had our attempt, of course, called the Manhattan Project, and it was a massive attempt by America and some of the Allies. Japan had their own attempt as well. Japan was trying to develop the atomic bomb. But Heisenberg, we have two main things, I guess, in my opinion, from the books I've read, two main things to thank the Germans not nuking New York City or Washington, D.C. or L.A. One was Heisenberg himself, who was heading the project. At the time, we didn't know it, but later on it came out that he was slow walking the progress. The other one is we have the Norwegians to help because they sunk a ferry full of heavy water that's used in moderators. And on that ferry were also, accounts of 500 or 600 women and children. The Norwegians, they killed their own people because they had to. Because if the Germans had gotten a hold of that heavy water, they might have gotten to the atomic bomb first. And so that's a story you should read about, maybe Wikipedia or something, about the Norwegians having to sink their own ship, it was a ferry across a lake. And the heavy water is this, it's a water molecules, but instead of having hydrogen, some of them are deuterium. And so deuterium is an isotope of hydrogen, so it's heavy. And that you need those for the moderators in these nuclear reactors. Anyway, so Heisenberg slow walked it. He did not want Hitler Heisenberg wanted the whole thing to be over. He did not want Hitler to have the bomb. He knew that he would use it on London probably first. And then, of course, you guys know Niels Bohr, the Bohr model of the atom, if you've had any chemistry at all, electrons and orbitals, and there's every one of these guys. Niels Bohr, Max Born was a great scientist and a great teacher. De Broglie back here, that's the French guy who figured out that matter can be either particles or waves. He figured he was a radio operator and used his radio wave knowledge to figure this out. He's another cool guy. Compton scattering, if you know much about that. So this is just, you could spend your entire physics career just studying these people. very exciting time in physics, and thought, well, in the Bragg equation, okay. I thought, well, it's 105 years ago this weekend, last weekend, when they had this in November of 1915. It's before the plague. I don't know how many of these old coots died during the plague, the Spanish. Oh, so, okay, do this differently now. And then, of course, yesterday, as far as announcements go, hopefully you saw this. They relaunched a perfect launch. Like I said, they're probably, I think they're docking right now. Maybe not yet. No, it's 27 hours. So they're not docking until later on this evening with the ISS, assuming everything's going well. But this is huge. I think we'll be back to the moon. I'm going to go along more on Elon Musk and think we'll be back to the moon by 2024. Some far projections is, I mean, starting to establish a base on the moon, not just going, taking a few pictures, planting a flag and leaving, but I mean, actually, going and start setting up a launch pad. So I think by 2050, we'll be launching from the moon for Mars. It's 100 times cheaper to launch from the moon. Now I'll open it up to question, how, or you answer, why would it be 100 times cheaper to launch from the moon than from the Earth? See, now that you don't have your cameras on, I don't know if you're awake or not, but we got to do it. So who has the answer?
Is it closer?
It's yeah, well, okay, fair enough. It's a little closer to Mars, depending on the time of month. Sometimes it's further away. What would be the reason, though?
Is since there's less gravity, would they
That's
need less fuel to get off?
exactly. So there's two main reasons. The main reason by far is there's less gravity. It's only 1/6 the gravity as Earth, the moon is 1/6. So things fall to the ground in 2 seconds here on Earth. It would take, 12 seconds. Well, it's acceleration, it's a little different, but it would take a lot longer to fall. There's a show called Away, I think, on Prime or Netflix or something. And there's one scene where the main character is throwing a ball in the air on the moon, like in the little hut they have, and it's real. I think physics, it's correct. The ball goes up perfect and comes back down in that slow motion. That's the way it'd be on the moon. So the moon doesn't have near the gravity to hold us down, and it's called a gravity well. So we don't have the gravity well to get out of on the moon. Also, there's no atmosphere, so you're not fighting air drag. You don't have that burn. Like you watched it yesterday, you saw that burning. Because part of it was the engines firing, I give you, but part of it, that burning, like when they come back into the atmosphere, that's because all the air is in the way. So once we get established on the moon, and I think this show Away is pretty good. It's kind of dramatic, but it looked like it is pretty good physics wise. So it's a good thing to watch. Anyway, once we're established in the moon and we have a base, then we can start launching like monthly from the moon. And we just found out a couple of weeks ago that there's plenty of water on the moon. It's in the regolith. It's not like a lake. There is ice in some of the shadows, but even in the soil, if we can harvest the hydrogen out of there and then separate the hydrogen and the oxygen, we can have rocket fuel. So we can be taken off. We don't have to take our fuel with us. So pretty exciting last night that was it was a combination of SpaceX and NASA, and that was a perfect launch. And we got we got the rockets back, so everything's working well. Oh, still not done with this page yet. So this week, tonight, I'm not going to do it here tonight from 9 to 10. And you probably don't want to spend 2 hours with me, but you can come tonight from 9 to 10 and ask questions, or you can just record it. And I will do this review here. I will do this in order. So it's not going to be like last time where, it was whatever you guys asked. And so we went kind of back and forth and all willy-nilly. This is going to be, here's number one, here's number two. And I'm not just working them for you, but I'm answering questions. So we'll start off with who has questions number one, and then we'll do that. And we'll go question number two. I'm not going to end up giving you all the answers, but I will get you a good start and answer any questions you have on all 7 of them. And then you turn it in, you submit it through Canvas tomorrow night by midnight. And then Wednesday, I'll do like I did on test 1. I know that was popular. That had 94 views on my YouTube channel. I only got 81 students. So, all right. Some kid from India is watching. So the video key, those are popular because that'll be me going over. Now, unfortunately, you've already turned it in, right? You turned it in on Tuesday. But Wednesday, though, you need to have, it's kind of a quick turnaround. You need to have it, you need to have a key for it to make sure that you did it right. Because I'm checking on this one that you turn in on Tuesday night, I'm going to spot check a couple of them, but most of them just giving you participation grade. So I don't want you to study the wrong thing. So at least fast forward through this if you have to, but at least spend 15, 20 minutes looking at this posted key, video key, me talking through each problem and showing you the correct way to do it. I'll do it as efficiently as possible. Try and keep it fairly quick. And then they take their test on the 19th. So we will not have, there'll be no wrap up this day on Thursday. So you can mark that off your list. No wrap up Thursday. Friday, then they will be watching Feast and Film, and I'll give you a link for you guys that you can watch it. I think it's on. It's always on the internet somewhere. Just the first part of our movie. It takes us like 3 or 4 attempts to watch the whole movie. And you all on Friday of this week will be taking the virtual test 2A. Now, I'm not going to make you come pick up the paper. Okay, I will send you. Now, if you don't have a printer and you can't print it off, then I guess you have no choice but to come get the printed paper out of your slot, from the box on the front porch. You have your own name slot. Brady, you don't have yours yet, but I'll get you one. So if you don't have a printer, let me know. Text me, and I will text me or message me, and I'll put the paper in there. So you'll take the test. It might be slightly different than the one they took in class, but it'll be very similar. And you'll get a PDF version of that. You'll take it. You'll give yourself an hour. You're been on the honor system there. You take paper and pencil, okay, because it's too hard. You cannot do it unless you have an iPad. If you have an iPad, okay. Otherwise, then you take a picture of it and you send it to me. You submit it by midnight. But you're gonna. I think what I'll do on there is once you start it, I can put a timer on it, and I'll put a timer. Maybe I haven't tried this yet, but maybe I'll make it like an hour and 15 minutes, so you have time to take a picture at the end, before you lose it. Maybe I don't know. I don't know how this works yet, but we'll figure this out on Friday. So by Friday, I'll have this a deadline. The actual deadline is midnight Friday for you to take that 150-point test, and then you're free for a while. So for this next week, and then if we come down here, this is in detail, more details there with like Zoom wrap up things. Any questions on all that stuff before we get going? You might end up with some questions as we get closer to Friday.
Andrew had a question in the chat.
Oh, okay. See, I cannot. I don't have much room here. Although I got a new monitor, so now I'm going to start to put that up so I'll have more room. Okay, thank you. If we want to go to school, yeah, Andrew, 100%. That is always true. He said, well, what if we want to go to school and just take it there? You can take it with first hour, with second hour, with third hour, or you can take it at lunch. So if you come into school to take it, you would have to have it done by 1 o'clock. Well, done, like started by noon, or let's say 1:15. Started by 12:15 then on Thursday, right? Friday's Feast and Film, and this is too big of a mess, too big a madhouse up there. I I can't watch you and watch, I can't do it. So it would have to be Thursday morning from 8:30 a.m. till, and I'll put you in the back room. In the back room, I can turn on this huge fan. And so, and shut the doors. And so you are isolated with a lot of air circulation in the prep room. So pretty safe place, in my opinion. So anytime Thursday, you can come in Thursday morning up till 12:15, and then started at 12:15, be done by 1:15. Okay. That'd be great. That'd be easier on me and you probably if you can do that. But if you can't, I get it. Okay. Glad you asked that. Now, this is mostly for you all, not really for my in-class kids. But with the weather getting more sporadic, like Friday, we don't really do things on Friday because Friday afternoon is my time to go ride my bike and just to kind of chill out and relax. But the problem is Friday, the weather was bad. And so I couldn't. I wish we would have much rather done it on Thursday. So I thought, okay, what we're going to do is we're going to do four sessions a week. But my free day will be floating. And I'll give you plenty of warning. But like if today was the most beautiful day of the week, I might have come today. But it turns out, coincidentally, that this week, Friday is the most beautiful day. So I got to have one day a week where I just go ride my bike and chill for a few hours and just think of nothing else. So it's going to work out fine, and Friday will be my day. So nothing out of the ordinary. But after Thanksgiving, it may, I'll let you know. Okay, so, whoops, I'm still not quite done with that yet. Hold on. I put in all the black and blue points into the grade book. So now I have, you may have noticed this, but I've dropped the cushion. So there was this fake 75 out of 75 point assignment just to kind of make sure people weren't failing. And actually, I have a few failing kids, but only 2 of them are really low. The rest of them are all close to passing. So I'm pretty happy with the way a lot of teachers have 50% of their students failing. So physics kids have held strong. The finger dance, if you're going to perform that live, which I don't think any of you would, that'd be Wednesday. But if you want to do it by tape, and really it's helped. I had one kid that spent a whole lunch with me learning the finger dance. And then when we did the stuff we're going to do in a minute, that he picked it all up because he goes, oh, I get it, because he pondered it. He forced himself to ponder, and that's what the finger dance does. It makes you think about what's happening. Anyway, I'll give you some bonus there. You don't have to do it, but you'd have to make a handmade tape of you doing the finger dance. And Bennett asked, well, I don't have a meter stick. I just have a little ruler. That's just too small. You can measure out a distance on the floor or something. You can make it twice as big, but you can't make your scale any smaller than a meter in length. Okay, you can double it 2 or 3 or 4 or 5 meters, but not anything less than. Okay, and then the pictures there. I mean, this is what I'm talking about. We're doing group 7, and then this is like people setting it up, trying to give you some hints there as to how you would do it. But you got to do a videotape of it, I guess, in your case, and get it to me by Sunday at midnight, or not. If you don't do it, you don't do it. Okay, this is Friday Feast and Film. There's a way for them to get points if they make food, and we got to individually wrap it. It's going to be a pain in the butt, but trying to be safe. And then we had Joke Monday. We did Dimitri Martin today. Okay. Now we are ready for today's topic. And today's topic is basically what I talked about. I'll go on to, I'll be a little more smoother, what I talked about on Saturday. So I'll just hit the highlights today and new things that came up in class. Okay, so refer back to Saturdays. That is probably the most important rapid video I made this year was Saturdays, because it has ramifications all the way up through May and all into Calculus 1, Calculus 2. Okay, so this was the ball rolling up and down a ramp, and it was a 3-degree ramp. So I'm rewriting this summer, but I have some notes to myself. And there are 3 key factors we're trying to find out in this lab. And one is, what is is V naught of the ball as it leaves the ruler. It gets pushed by the ruler. 2 is what is the acceleration of the ball, and 3 is how much do we dilute gravity? How much dilution? How much dilution of gravity? So I'm using the terms that Galileo chose. How much is our dilution of gravity? We dilute gravity so we can slow it down. We could go to the moon, I guess, but this is easier. Just put it on an inclined plane. And then at the end, I think in here, we didn't even get this far in many classes, but at the end, we'll do a little bit with that, if we're looking good on time. Okay, I talked too much about the Solvay. All right, so this one, we started this and we did some of this, I think, on Thursday. But I'm going to go through this kind of step by step. And there'll be screenshots on this. So if this doesn't show very clear, but we're looking at how the ball changes. So it's a trio. Anytime the acceleration is constant, it's a trio. And acceleration is constant when only one force acts in the direction of motion or partially in the direction of motion. The only force that acts in the direction of motion here is gravity. Now it's not rising, it's not directly against or for, but it's the driving force, if we're going to call gravity a force. We're looking at classical physics. So classical physics considers gravity a force. Einstein, modern physics considers gravity a measure of curvature of space. But we don't have the calculus yet to really mess with the Riemann equation and all this stuff that Einstein uses. So it's easier, it's more Newtonian to think of, for us, think of gravity as a force, this invisible force that's pulling things down to earth. So, but that's the only force. If you assume friction is minimal, there has to be some friction or the ball wouldn't rotate. The ball would just slide, but the ball does rotate. So there's some friction, but we're assuming it's a low amount of friction. We're assuming no air drag. It's not fast enough to have air drag. So really by far the dominating force here is gravity. Therefore, if you only have one dominating force, you have one thing that's, so your acceleration is constant. And so if acceleration is constant, we're dealing with a trio. Okay. So flat. So in a trio situation, we have flat on bottom, we have linear there above it, and then we have parabola here, right? But this situation, gravity is pulling the ball back. Like the ball leaves the ruler and it's heading up the ramp and it's being pulled back by gravity. So that makes this bottom in the fourth quadrant, which makes it negative, which then turns this around and makes my V versus T negative slope. Negative slope, very sloppy here. And then it makes this a negative parabola. Well, it's still parabolic, but negative. So that would put it like this, right? Instead of coming up like that, it's coming down like that. But something else happened. I came back to the origin. So I started here at the origin, came up to the apex, and then came back down, okay? So this is more like what this graph will look like. So you got to know the general shapes. And it makes sense because the green here is the tangent. And so the tangent lines hit that curve at one point, and they tell you what's going on curvature-wise at any given instant. So you can see that these green tangent lines are getting less and less steep and finally they go flat. So it goes from this very steep green tangent line to this flat one. Now the slopes of these tangent lines is our velocity, okay? But thing is, Newton didn't either. Newton didn't trust himself to draw the graph, to draw the tangent line correctly, because it's like a teeter-totter. You know, you're teeter-tottering on that one point. Well, is that the correct? Maybe it's off a little bit. So we'll show you some of the trickery he came up with. So the ball starts off moving the fastest it's going to move in the whole thing. When you let it go from that ruler, it's going, this is the steepest it's going to be. And then as it goes closer, it slows down. Okay. So then we can go, because of symmetry, we can go ahead and complete the parabola. Because we know if it goes up, and this is called the axis of symmetry right here. This is the axis of symmetry. Now you always look for axes of symmetry in physics and organic chemistry and physical chemistry. You're always looking for axes of symmetry. Like in class, we got to talking about the water molecule. Well, the water molecule has an axis of symmetry, and it's those axes of symmetry at which the water molecule rotates about. So the water molecule has 3 degrees of freedom. Well, it has more than that, but it has 3 categories of degrees of freedom. You know, it has translational, it has rotational, it has vibrational. But as far as rotating, that water molecule can rotate around and around this axis of symmetry, and it does. A water vapor molecule, and water even in liquid form. There's a guy named Alberto Strillo. And Alberto, Dr. Strillo now, when his research for his PhD, he was in chemical engineering, but he would come and talk to the class every year. And sometimes they'd bring his mama and the papa with him, and then they'd bring the pizza. I kid you not. I'm not being stereotypical. This is Alberto. Anyway, so what he studied water molecules, and that's what he did. Just studied water. Kind of cool. But he looked at it on molecular. He looked at what's called water clusters. So water molecules, when they get in small amounts, like I'm talking micropipettes, little smaller than a drop of water. When they get in these where they have 30, 40 water molecules, of course, there's billions in a teaspoon. But when you get the water molecules tend to act differently. And so why he cared about how that is they're going to start to deliver medicine, right? They're already doing it now, but through patches, this nanotechnology, so that you'll get instead of getting a vaccine, they'll throw a patch on you. And in there, you'll have these little tiny needles that you can't even feel, they're so small. And water, of course, most things use water, right? So water will be what's the solvent. And so it'll go, so the water though, when it goes to those they act differently than a water does through a pipe. So point is, sorry, getting off on that. The point is, Alberto had to study water molecules and how they revolve. So this is a practical situation where axis of symmetry is very important. And by the way, here he had to look at the omegas, right? How many radians per second is those water molecules rotating? All that kind of stuff. I'm just saying there's ramifications to everything we do in here. He spent his whole life studying. Okay, and eating lots of pizza. So we keep going. So all these tangent lines, they're kind of like little pixie sticks. All right, and they get steeper, then they get steeper symmetrically the opposite direction. Of course, your apex there. Well, now we're going to plot this. And we talked, I know I sound like I'm repeating myself, and I am, because these are so fundamental things we keep hitting again. You plot the slopes of the tangent lines here, and anything in this first quadrant would be forwards. Anything in the blue or the fourth quadrant would be backwards. So in the class, I demonstrated the ball, and I'd say green, 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 and then it hits the apex, blue, 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 on the way back down, what quadrant it's in. And we also know that since this is parabolic right up here, this must be linear, negatively linear. And so sure enough, it's negatively linear. But the question is, I don't know what that value is right there. I don't know what the initial velocity of the ball is. I know what it looks like. So I just kind of stuck it somewhere and then used my laws of symmetry. Remember, that's the apex right there. So that's the point at which the marble turns around. That's where the velocity goes from the green to the blue. It goes from the forwards quadrant to the backwards quadrant. So it's 0 temporarily. Okay. And there's my general equations. You know, in this case, it'd be negative, and this would be negative. The V naught is positive, but the A is negative, okay? And there, A naught is negative. Okay, so this you can split this up into the ups and the downs. Now, calculus would call this green area positive area. They call the blue area negative area. But the ups is like if I throw a ball in the air, it would be in this. And by the way, this is a perfect bow tie. You see where this is a bow tie, like you'd tie the tie. It's a perfect bow tie. So the green is the time it spends going up, and the position it changes, and the blue is it going down. So when I first learned about negative area in calculus, it kind of freaked me out. I remember in high school, Mr. Gilmers was talking about that. I said, I don't understand. I could not get my mind wrapped around negative area. But it is negative in that it's things like it's in the fourth quadrant. So position is negative. Time isn't, but position is negative. Sorry, wrong, dumb. Not position. Velocity is negative. Position throughout the whole, in this experience, position was positive the whole time. Because it never went further past the origin. So it's called a perfect bow tie. And then what about a situation where I throw a ball up, or let's say off a building, and it lands in the ground below? What would that bow tie look like? So sketch it on your paper, and then I'll show you what it looks like. What would the bow tie look like? I'm talking about velocity versus time for a ball that you throw up in the air, and then it lands, say, 2 stories below you. You don't need to say anything. Just draw it on your paper, and then I'm going to show you the answer. Okay, you ready? I think this is it. Yeah. So this is called a skewed bow tie. And here, of course, that's the apex. Now I'm getting into stuff we're going to talk about December and maybe January. There's the apex. And so once again, the ups is not very big there, a lot more downs. So these are skewed bow ties. Used in projectile motion, used in free fall, used in any sport involves skewed bow ties. And then one more to play with this. What if we throw, like someone says they're in the 2nd floor and they say, hey, throw me the keys to the car. And so you take them out of your pocket and you throw them up there and they reach their apex and then come back down and they get caught by the person out of the window. They stick their hand out and they catch it on the way back down. Sketch what that would look like. It's real important. I know you're sitting in your living room or something by yourself and no one's checking on you, but you ought to, do it. Check it. Try it. That way, if you're wrong, nobody knows. All right, so this time we're throwing it in the air. It's reaching its apex. Then it comes down and somebody in the 2nd floor window catches it. Are you ready? Here we go. Throw it in the air. Up, apex. Caught. So that looks like this. Green area, the ups, and then blue area, the downs. So this is catching it right after it hits the apex. All right, so if you picked up on that, that's pretty good for this time of year. Right, but in our case, it went up and came back down right where it took off at. So it's a perfect bow tie. Once again, though, what is this value right here? What is my initial value? And we talked about this briefly. So in other words, what's the initial velocity of the ball? Okay, so remember that the graph above this graph is showing you the accumulation of area of this graph down here. As I go from left to right on this graph, on the area, okay, as I go left to right, I am still gaining green area, but the amount I'm gaining is decreasing as I go. So we're going to have to, so what we have to do is find the area of this green, to find the height of the green right triangle, we have to find the area of the green right triangle. So remember that from geometry, the area of any triangle is 1/2 base times height. So the base here I know is 3.3 seconds, okay? The height, I want to know that. I know the area from this because I know the area of this green triangle, this graph down here, is this area up here being accumulated. I already know, and the kids in class knew this. I asked them, they all said 200. So boom, there it is, 200 centimeters. So I already know what the area is. So now all I have to do is use the formula and find the height of the triangle. And so you have area equals 1/2 base times height. Height then is 2 times the area over base, just multiply by 2, divide by b. And then I get 2 times 200 over 3.3. So I'm getting 121 centimeters per second. Now, when I first did that, I thought, oh, I made a mistake. That's too fast. But not really. The ball, that's about the speed at which people walk. So it's not that fast. The ball left, the average student, the ball left their ruler at about that speed. So now finally I can fill that in. That's 121 centimeters per second. So that was one of the things I wanted to do, was find out what the initial velocity of the ball was. Let's get past this one. Let's go right to this one. Now, this will be on a screenshot so you can blow it up and write the stuff down. But we talked about front end loading to front end load. And that's what this is. In this situation, the velocity is front loaded. And so you start off going really quickly. In the first 1 second here, I gain 125, this area, remember this is the area up here, I gain 125 centimeters. So my orange represents what's happening on the x versus t during this velocity versus time. In the second, I'm doing, that's the orange trapezoid. Now the blue trapezoid you can see is not nearly as big. And that represents the area of the second, or in other words, the change in position. Well, this, if I found this area, I end up at 175, but I started at 125. So I've only gained 50 centimeters. So in the first second, I gained 125 centimeters. That ball did. In the second, it only gained 50 centimeters. And then we go to the third second, it's really the third 1.3 seconds because it got to the apex. So in that third 1.3 seconds, it goes from about 175 to 200. So it only gains 25 centimeters. So the gain keeps dropping because gravity, although very weak, well, it's not that weak on Earth, it's decent. Gravity's saying, come back. Even though it's diluted, it's saying, come back, come back. And it finally wins out at 3.3 seconds, and the ball starts to roll backwards, back to the origin. So now that we figured out all that stuff, now the easy part is to find the acceleration, and that's simply just finding the slope of this line. So so just find the slope of the line, and we'll just go back to what we do in day 2 in class, or day 3, and that is figuring out rise over run. So my run here is 6.6 seconds. My rise is really a fall. But where did I get 242? A student asked today.
It's double the 121.
Double the 121, right? Because it went up, came back down. So so the velocity started off at 121. It ended up going at negative 121. So the speed the ball takes off up is the same as the speed it comes back down. Now that's why in Mexico, like for birthdays and stuff, one of the customs there is not all the time, but some people shoot off guns, right? Woo, woo, bang, 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 in the air. But I don't know how many hundreds of Mexicans die a year. And I say Mexico because I know they do it, maybe other countries too, but I don't know how many Mexicans die a year because that bullet leaves at like Mach 2 and it comes back down. And when it comes back down, that slug is not moving near that speed because of air drag, because of the deformation that occurred. It's not as aerodynamic. But when it comes back down, it goes into people's skulls or hits them in the shoulder. And so people end up in the hospital and they die because what goes up comes down. Well, the same thing here. But we're saying perfect, no friction, no nothing. So we're saying it comes back down at 121 centimeters per second by the time it gets there. So that makes it negative 242. So we have negative 242 divided by 6.6. We have rise over run. And when we do that, our math here tells us that we have, that ends up being negative 36.7 centimeters per second. So that is how much that ball, that marble, I can't say slowed down because sometimes it was speeding up, right? Slowed down to the apex and then sped up from the apex back to the origin at 36.7 centimeters. Well, okay, it's hard to know what that means. So we compare that to gravity on Earth. Well, gravity on Earth is 981 centimeters per second per second. So we really diluted gravity. And to see how much we diluted it by, there's a little formula here. It's called percent difference. So we take the 981, we subtract the 37, we divide that by 981 times 100. And we diluted gravity in this inclined plane by 96%. That's pretty good. Put it on a 3-degree incline. 96% of the effect of gravity was taken away. So it's still there, but we slowed it down. We did what Galileo said, we diluted it. Okay? Now, okay, so that's how we ended most classes today. In first hour, we got to this a little bit. So let's talk about this briefly. Oh, we're almost done. We're almost done. So this is another way to do this, another way to determine acceleration. And this was 3 degrees. I better be careful on what I say here. Okay, well, I'll talk to you guys. So, all right. So G, acceleration is a vector, right? So G is 981 centimeters per second squared. And that's, and if I'm plotting acceleration vectors, that's straight down towards the center of the earth, right? Yeah. Okay, I'll keep this simple. I'll keep it simple. Good. I'm gonna see if I can find a fast way to get to that answer without going through all that trio stuff. I don't know. You're watching this for the first time. It may not work. Okay, so this, I'm gonna make a right triangle out of this. A tilted right triangle. Oh, you're gonna love that tomorrow. A tilted right triangle. I'll color in my right triangle. Let me blow this up again. Color in my right triangle. You guys should play along. It's fun. Hold on. Okay, turn it off. All right, so I'm color this in. This is the right triangle I'm talking about. Your right triangle should emanate from the axis that you're interested in. I'm interested in the x. What's going on the x-axis? All right, so this hypotenuse is 981 centimeters per second squared long. I want to know how long is this? How long is this side? Change colors. How long is this red leg? if the hypotenuse, now, little geometry here. If that's 3 degrees, if this is 3 degrees, and we come up here, and that's 90, okay, by definition, that is 90. This angle right here is 90, supposed to be. Then what would this angle be?
87.
87. So that means that this whole angle, corresponding angles are also congruent. So this is, let me clean this up a little bit. All right, so this is 87 degrees. All right, now, if I want to know the amount of gravity down the incline, which I am saying back from all that work I did, I finally concluded that that amount of gravity down the incline, the amount of acceleration was negative 36.7, right? That's what I claimed it was. Now let's try this with a much simpler approach and tell me what is, this will be our acceleration, A sub X, we'll call it. The hypotenuse is 981. That's this leg, not the leg, the hypotenuse. So this is 981. So now it comes down to simple trigonometry. If the hypotenuse is 981 and the angle's 87, what is this side? And how do I do it? And my hint is SOHCAHTOA.
Isn't it
Cosine?
981 sine 87?
Wouldn't be sine because this is the adjacent side, right? That's the adjacent to that 87. This is the sine part. So yeah, it'd be 9, but you're right, you're on the right track. It'd be 981 centimeters per second squared times cosine of 87. Now make sure you are in degrees and not radians. You have to be in to make sure your calculator doesn't have a RAD on it. When you punch this in, what do you get? I don't know. I'm curious. Come on, baby. Come on, baby. Please be close. Physics works.
I got 51.34.
All right. So you
Me
got
too.
51.3. Let's just say 51. Oh, I will say 0.3 centimeters per second squared. According to this, theoretically, without doing any lab at all, we should have got 51.3. Instead, we got 36.7. So now we see how far off we are. Now remember, we are in the real world. We were using timers. We had friction. Let's see how far off we are. 51.3 minus, this is what's called a percent. Okay, this is called a percent error. Percent error. We'll get into this heavy after Thanksgiving. I'm just making that sheet up now. By the way, I'm putting together 211 through 216. Remember I told you I was going to extend Pkt2? So I'm putting the finishing touches on 211 through 216. I have to go finish those off, print those off, and then get them copied off. And they'll come together with a little staple packet. And that'll be an addendum. That'll be what you're going to staple. You will then staple that to your 2.1 through 2.10. You're not going to turn it in till like right before Christmas break, winter break. All right, they'll turn it in then. But I'm just telling you, that's going to be available starting tomorrow. And I'll put some on my front porch. If you don't want to print off 6 pages, I'll staple some together, put them on the front porch in the handouts box. Anywho, so percent error, we said that was 36.7. So minus 36.7, you subtract, and here you don't need to put units because the units will cancel anyway. And you divide it by, so you take the real number, it's absolute value up here. Take the real number, what theoretically should be the number, you subtract your number, and then you divide it by the real number, 51.3, And then you multiply the whole thing times 100. And what do we get? Let's see how far off we are.
I got 28.4 or 28.46.
So about 20, so times 100, right? So we were about 28% off. Well, I've seen labs that are 200% off, you know? And so it depends. To do this right, we would have had to get photo gates. And I was, to be honest with you, I was just saying that, like here, I was saying, let's just round it to 6.6. So I was doing a lot of arm waving back here. Let's call it, that'd be 3.3. Let's say that it went 200 centimeters. So, you know, that's ballparkish where we were. But considering it was all ballparkish, 28% off isn't that bad. I know it sounds bad. Generally in high school, you want your labs to go to, like if you're really measuring things, you want your labs to be about within 10% error, no more than 10% error. In college, more like a 5% error is still somewhat acceptable for a physics lab. In grad school, we're talking 1% error, 2% error at the most. And then you got to account for all that error, okay? But they have better instruments and they take into account other things, coefficients of friction between the marble and the ramp and all that. So I'm pretty happy with that. It's okay. Always should be a little better, but that's fine. Okay, so I'm going to stop sharing unless you had a question about a slide. Any questions? You want to go back and look at a slide? Okay, so stop the sharing here. Any questions about what's happening this week? Don't forget tonight at 9 o'clock, 9 to 10. We'll go to 10, I guess, unless we finish early. Will be me answering questions in order 1 through 7 on the take-home test. I'll record that, and that'll go into Facebook. I'll put a link in Facebook, and I'll also put a link in the Canvas, and it'll be in the YouTube channel. Just subscribe to YouTube. That's where all the videos go. And then it's due tomorrow, and then Wednesday you'll see a posted video key, and then Friday you'll take the test. Okay, so don't turn your camera on, but any questions? I'm about to stop recording. Okay, so this officially ends